Good afternoon, ladies and gentlemen. Our topic 3 today is the purpose of preventing unplanned losses, understanding why we need to seal critical interfaces such as around windows and doors. Thank you for joining us.
Good afternoon, everybody. I see some familiar faces have joined for the third part of this coffee chat series. So welcome back, and welcome to any new faces. For those of you who don't know me, Rob Halliwell, Specification Manager for the Windows and Facades Division of the Ilbert brand CPG UK Limited. Let's get straight on with it. Now, several studies have been commissioned and completed by the likes of the BRE, BISRA, the Fraunhofer Institute and IFT Rosenheim, proving that even minor emissions and poor sealing strategy can lead to major losses through unplanned air loss, infiltration and moisture migration. This is the essence of the standards of BIN 4108 and BS 5250. The window interface junction is a particularly vulnerable area, and the same losses occur through the framed and sheathed wall, which is so very often sealed just with an emphasis on water ingress that the requirements for air tightness and adequate vapor control are often overlooked or misunderstood. We tend to forget that our buildings move and expand and contract, and inevitably some hidden, less obvious seals fail at the building connection joints. Nevertheless, let's take a look specifically at the window interface and see how these losses occur. Now, let's assume that our window has been sealed using more traditional methods, for example, a simple PU foam and an external silicone sealant. We know that traditional sealing methods are less efficient and begin to degrade over time, sometimes prematurely. Now, if the ambient temperature of a room with a gap to the exterior contains the same air at the same temperature and pressure as the outside, there'll be no significant movement of air until the heating system is turned on. The act of heating a room creates a pressure gradient from inside to outside, causing the rising internal warm moist air to exit the room via the gaps in the structure. As it does so, cold air from the outside is drawn through any gaps in the lower region and displaces the lighter warm air as it rises, forming convection currents. This may be even more pronounced where two or more gaps exist, one above the other, as a chimney effect can be created with the cold air infiltrating through the lower gap and the warm air escaping through the upper gap. If the temperature is set high, or if the heating system is efficient, then the pressure gradient is more exaggerated. The convection cycle is faster, and hence the convection heat loss is actually greater than at lower temperature settings or with a less efficient heating system. Bearing in mind that building regulations set the standard air tightness test pressure of 50 pascals, these events are especially significant if the leak is formed between a high-performance wall and a high-performance window, because the leak becomes the focal point of energy loss and could constitute almost 100% of the total convection leakage. As well as air infiltration, these gaps enable a phenomenon known as an open thermal loop bypass, where, in relatively windy conditions, the wind washing against the building fabric forces cold air into the building through the open interfaces, pushing the warm air out, thus increasing and accelerating the convection heat loss through the gaps. Under these conditions, it's difficult to quantify how much heat is lost through air leakage or infiltration, or even through the smallest gaps. Now, air loss and moisture migration still occurs even at lower pressure differentials. The graphic represents an experiment carried out by the Fraunhofer Institute in Germany. With the ambient air temperature set at 20 degrees and relative humidity of 50%, there was significant air loss recorded and migration of moisture at only a pressure differential of 6 pascals in a 1 millimeter wide joint. Now, 6 pascals is approximately 1/6 of the apparent test standard of 50 pascals. The thermal conductivity of 5.1 WMK demonstrates the potential losses in a poorly or partially sealed facade construction joint, or the tolerance gaps between the glazing frame and the structure. Now, think how many penetrations there may be through a vapor control layer by default, and how many butt joints there are between sheathing boards and insulation slabs on a high-rise building with an SFS infill. The expanded experiment went on to assess the effect of air loss on U value. A sealed 1 metre by 1 metre cube was constructed and lined with 140 millimetres of insulation. The construction has calculated U value of 0.3 WMK. The cube was pressurised at 50 pascals and the U value was then confirmed. In the second part of the assessment, a 1 millimetre wide by 1 metre gap was created in the construction. It was then repressurised. On completion of the assessment, the U value had risen to 1.44 WMK, which means that the air leakage meant the insulation was 5 times less efficient. Now, warm air carries moisture vapour through the layers, and when the dew point is met, the moisture condenses, leading to interstitial condensation, which can manifest itself in any of the fabric layers, including the insulation layer. Whilst combined U value and condensation risk analysis is routine, there is a failure in the traditional methods of calculation known collectively as the Glaser method. The Glaser method assumes a static state through the centre of layer set of wall components over a period of time, e.g. the seasons, and a range of average recorded seasonal temperatures for a generic set of UK geographical regions. Whilst helpful, the Glaser method cannot take into account liquid water or water vapour transport, nor can it take into the account of air leakage. Instead, its calculations are based on a theoretical thermal and vapour resistance of individual layered components in one direction only, either horizontally or vertically. The calculations do not take into account, they do take into account spaces such as air gaps that make up the cavity or surface voids, but not the throughput of warm, moist air and the effect of liquid water ingress from either side. Consequently, the difference in the as-built outcome may not mirror the design intent. This is known as the design gap. So we bring us on to modern ceiling theory of inside tighter than outside. So there are 3 simple rules for windows and doors. Internal seals, membranes, should be more vapor tight than the external ones. So for a window and door, we ought to have an internal perimeter, airtight, weathertight, vapor closed seal, which may have variable vapor permeability, or known as an intelligent function. We should have an external perimeter membrane, which is also airtight and watertight, but vapor open, or again, may have an intelligent function. More importantly, a primary weather seal, which should be flexible and weathertight, but vapor open, is often preferred, such as Ilbrook Compraband. 2 simple rules also apply to the structure. An internal membrane, airtight and vapor closed, with a vapor resistance of at least 250 meganewton seconds per gram, or an SD value equivalent thickness layer of 50 meters. On the cold side of the wall, externally, we should have a weathertight, watertight, vapor open, and preferably airtight membrane. Vapor closed membranes are most often applied to the internal framed wall between the internal finishes and the insulated framework that makes up the wall. The purpose of a vapor control barrier membrane is to provide a physical separation layer between the warm, conditioned internal environment and the cold, unconditioned external environment beyond the separation layer. The vapor control barrier, often a membrane made from polyethylene in an SFS or framed wall construction, is an item or a product used to form the separation barrier, which then creates the vapor control layer. Its function is to significantly reduce the migration of warm, moist air through the wall fabric layers from the warm side to the cold side via the pressure differential that was described previously. A vapor barrier can be any highly vapor-resistant material. Polyethylene is the most convenient and often the most common. A vapor control barrier must have a minimum resistance to vapor diffusion, usually described as vapor resistance measured in meganewton seconds per gram, or MN/S.G. The higher the number, the more vapor tight the layer is. Vapor control barriers should achieve a minimum resistance of 250 meganewton seconds per gram, according to the CWCT BRE Building Regulations Part L and accredited construction details. Vapor resistance is also measured or expressed as an equivalent thickness layer, or SD value. Again, the higher the number, the more vapor tight the material is according to its thickness. SD values are expressed in meters. A material of 0.1 millimeter thickness can have an SD value of 107 meters, which is very vapor tight, but equally another material could be as much as 100 millimeter thick and have an SD value of 0.04, which is highly vapor open. Now, the difference between the two demonstrates the difference between a vapor control barrier and a typical breather membrane. Hillbrook offers a complete proprietary vapor barrier membrane system, Hillbrook ME003. Hillbrook also offers another product in the category of vapor closed membrane, ME480BB, a highly vapor-tight membrane that is completely airtight and resistant to driving rain. ME480 is used as an alternative window and door perimeter sealing membrane that has a Class B S1D0 reaction to fire. It is the preferred solution for internal window and door sealing applications that require compliance with approved document B. ME480 is not used as a vapor barrier in the commonly understood sense of a VCL. It's a dedicated internal seal added to the perimeter and is then linked to the structure and the primary vapor barrier membrane. Together, they make up the vapor control layer. ME480 can also be used externally in special circumstances. A breather or breathable membrane describes a function rather than an individual product. Breather membranes are commonly used as a monolithic covering to protect the elements of the backing wall and can be placed between the insulation and the sheathing board or directly over the insulation. The latter is technically more desirable and beneficial, but less often employed here in the UK. A breathable membrane is a membrane that is available in a variety of slit widths and is also used as an external seal as applied to window, door and curtain wall perimeter joints. A breathable membrane and a breather membrane should resist liquid water penetration but allow moisture to diffuse through it. Diffusion is required because of the changes in relative humidity and resultant saturation pressure on the cold side of the wall, where dew points are lowered and are highly exaggerated beyond the heated, conditioned environment of the occupied spaces. In respect of the resistance to liquid water penetration, Class W1 is the highest performance available for a sheet material that's used as an underlay or as a proofing layer. Monolithic breather membranes can also be airtight, but most commercial versions in the UK are not. The Hillbrook breather membranes by default are airtight, which is an added technical bonus. Hillbrook currently provides 3 solutions in the category of breathable membrane, 2 versions of a product called ME010 facade UV and fire membrane, and ME011 breather membrane UV. ME010 is available as a monolithic sheet material supplied on a log and is used as the primary breather membrane to protect the backing wall. ME010 is also available in a variety of slit widths to provide a membrane seal to the external glazing perimeter between the glazing frame and structure. It's bonded to the frame and wall with a paste adhesive. ME010 is our default approved document B compliant solution for external solutions. ME011 is used as a monolithic breather membrane for non-relevant buildings only, where there is no required compliance with approved document B. Now, this is an example and an explanation of an intelligent membrane, which is a membrane that is airtight and resists liquid water penetration and is also breathable, but in this instance, its ability to allow vapor diffusion is variable. The intelligent function describes the membrane's reaction when conditions change. Instead of being permanently vapor open, the membrane will become more vapor tight when placed in an atmosphere with high relative humidity, such as internally on the occupied space. When placed in a lower saturated environment with less relative humidity, such as the cold side of the wall, in the cavity space or an insulation zone, it will become more vapor open. If there's a dramatic or unusually high change in atmospheric pressure, the membrane will intelligently react and will either become more vapor open or vapor enclosed to ensure that no interstitial condensation becomes trapped around the window joint, permitting it to dry out. An intelligent membrane is usually used to seal around the window, door or curtain wall perimeter. Placing a heavy duty version around the external perimeter and a light duty version around the internal perimeter ensures that the high performance windows and doors can maintain their U values. This is achieved by ensuring that the focal point of air loss that we discussed earlier and moisture migration at the perimeter gap between the frame and the structure doesn't lead to localized interstitial condensation. Intelligent membranes are formed with two layers, a polyester outer layer and a very thin microporous polyethylene layer on the reverse. Intelligent membranes shouldn't be confused with the breather membrane or a vapor control barrier membrane. Intelligent membranes are incorporated into both respective layers and have a breathable function and a vapor control function, but they are not breather membranes or vapor control membranes in the commonly understood sense. Breather membranes are constantly vapor open, and vapor control membranes are permanently vapor closed. Intelligent membranes are calibrated for small gaps and are not monolithic envelope coverings. Ilbruck offers two primary intelligent membranes, ME501 Duo HD with some variations, and ME508 Duo EWF. So returning to our original diagram from the beginning, we can see how the loop can be closed by applying the appropriate measures. To comply with inside tighter than outside and to close the potential open thermal loop bypass, 3 seals are required at the window door interface. External primary weather seal between the frame and the cladding. Now this may be breathable, such as an impregnated expanding foam tape or Compraband, our branded product. The second seal, an external window perimeter, the airtight breathable or intelligent membrane, which then interfaces with the external primary breather membrane. Lastly, an internal window perimeter membrane, which is completely air and vapor tight or may have a variable vapor function, and that interfaces with the main vapor barrier membrane. This is the essence of the Ilbruck BBA accredited i3 system for framed and sheathed walls. Do we have any questions?
Right there, ladies and gentlemen, we don't currently have any questions, Rob, in the question box. So what I would like to say is really, if you do have anything and any thoughts and would like to reach out to Rob, you know, after this coffee chat's taken place, then please email Rob Halliwell directly. And thank you very much for your time today.